Okay, great. Welcome back. So maybe show me your faces, start your cameras. Any questions concerning the small exercises, anything to discuss you want to raise here? Don't be shy, please. Let's interact.
Yeah, Heiner, we had a good discussion about the time reversal symmetry notebook, and I did a very bad job trying to invoke some kind of like special relativity type argument for why you can see waves outside of the sphere of instruments that are in the time reverse thing and not in the outward propagating. And I tried to say, oh, like, you know, that wave field doesn't really matter inside of the array because outside of the sphere of influence from the time that's relevant. But I did a very bad job of it. So maybe you could explain better than I.
Yeah, no, good point. So your background is physics, right, Jack? Many of your background is physics. Can you let me rephrase your question? A great question. What do you think would be the condition under which you would probably not see this if I understood correctly, in the time reversal, you see things going outward, right? So that should not be there. Let me rephrase the question. Under what condition do you think those would not be there? What's the condition for this to work perfectly? Could anyone give an answer to that?
We tried experimenting with increasing the number of instruments to improve constructive interference, but I think it just ends up with like being a circular explosion source outside. So that doesn't help.
So I have, I didn't try this myself, and I answer this out of my belly to some extent. But I think if you would have an infinite, continuous boundary of receivers, it should, that's one answer, it should perfectly, well, in any case, then it would, in the time reversal, it would be a perfect spot. The other thing is this Huygens principle. To some extent, if you inject something, or if you have everything is a point source. So from each point you inject something, you will get a point radiation. So that's a little bit like the Huygens principle basically says every point on a wavefront is in itself a source. And it's kind of the same thing. If you think you have a circular wavefront and you discretize it, it's not like we will see later an emanating wavefront. If you then discretize it and you inject individual sources, you would also have sources that go travel inside, inside the circle, which you would not have. But you don't have that if you have a perfect, let's say, a complete representation of the wavefront. I'm not sure I'm answering this rigorously, but yeah, it's a good question. So what is important? Remember this Huygens principle. Every point in a wavefront in itself is basically a new source, and it's the superposition of all those that creates then, let's say, a unique wavefront that's propagating the constructive and destructive interference. So it's interesting to try and do this numerically, but of course there was not much time to really increase the number of of receivers towards infinity, and that should make a difference.
Yeah, we tried values of 5 and 1,000, and you can see as you get up towards 1,000 receivers, you get a perfect spot in the center. But it doesn't. I think it just also trends to getting a perfect circular outgoing wave as well. So it's interesting to experiment with anyway.
Okay, so I don't think I answered properly, but it's a good question. Any other issues that came up in the discussions? Okay, then let's move on to the second part. We share the screen. Presentation mode. Can you see that? Everything good?
Yeah.
Okay, thank you. So let's get started. So this is part 2, and we now want to go into the specific methods. Again, with a relatively, well, there's a typo, spectral, relatively condensed. The important thing is I want to show similarities, differences between these methods, and also motivate that basically in the end we took the best of all worlds to come up with the spectral element method. The spectral element method has partly finite difference methods for the time extrapolation. It has aspects of the pseudospectrum method for the interpolation and so forth. So that's kind of the idea. The picture here you see is I'm not sure whether some of you have seen this before. That's a picture of the connection machine CM2. It's a bit of history, but also personal history. When I started a PhD project in Paris 32 years ago, this computer arrived 3 weeks later. And it's the most beautiful computer ever built, I think. And it was a parallel computer. And by the way, this bench to the right is a 20 gigabyte memory part. 20 gigabyte memory. I don't have a today you can buy, I don't know how many gigabytes on something like this. This was the so-called data vault. It contained 20 gigabytes. I always like to show that. It's quite amazing where we are today compared to that. But this is one of the early parallel machines with 60,000 different processors. So parallelization is an issue. We've learned that it's expensive to simulate seismic wave fields. We need to have parallel algorithms, and that's part of the things why it's interesting to discuss this in a historic context also, because some of the methods lend themselves well for parallelism, some don't. Okay, so we start with a finite difference method. Probably most of you have seen this before, so I think we can be relatively quick on this one. So let's first look at the picture. So this is like in a nutshell. This would be a one-dimensional domain here, and what you see is an actual simulation of a pressure wave field. Pressure as a function of x. So you have a vector here on which you describe the pressure field, for example. And of course, at some point, you, for example, need the second derivative in space. You will have a grid. This is called a grid method because we have a regular grid. These would be these points, the black points, on which we know the space-dependent fields. And the derivatives are calculated by taking information. If you want to calculate the derivative here, you take information at this point and at this point here. So I minus 1, I plus 1. The upper index j stands for time step j. and divide by dx over 2, and you have an approximation of the second derivative of point P. Very simple, very elegant. It's a direct, so-called direct approximation of the partial differential equation. And here's another term. It's a local computational scheme. Local in the sense that if you think that each of those points would be on different processors, that means I have a near neighbor communication. That's very, very important from a computational point of view. So I only have to look in a processor next to me. And in a large supercomputer, the physical distance between information on the processors is very important. What makes an algorithm slow is if you have to look far for information. For example, think of the maximum value of a matrix distributed on a whole machine. This is a global communication because you have to compare something with each processor. Very inefficient. This here is a local operation. That means these kind of finite difference calculations lend themselves for parallelization. Very efficient on regular grids, strongly heterogeneous models. And by that, I mean with strong geometries can be more difficult. Boundary conditions, I mentioned that. The free surface boundary condition in finite differences is not so easy to implement accurately. That's a disadvantage. And that's important. It's the method of choice for flat topography and moderate velocity perturbations. And also, in particular, when you have primarily body waves that you're interested in. What's the most important application of this? Exploration geophysics, reservoir modeling, okay? Not necessarily regional wave propagation, where you have a lot of surface waves. They are very efficient extensions. I will mention this at the end, but they are unfortunately rarely used. I make a statement here also from the very beginning. You can beat spectral elements easily with a finite difference algorithm if you do things right. Okay, that's not the way it's communicated in a lot of spectral element papers. But I could show you for certain applications, finite differences is better than or more efficient than spectral elements. But again, that's not usually what's written in the papers. Okay, simple example. We take the acoustic wave equation. We've seen this before. We have a second time derivative. We have a second space derivative, one dimension. Let's do it really simple. And so what we do is we replace, first of all, we know the dependencies. Again, we've seen this before. And the first step always is we have to discretize space-time. So here it's very easy. We just say, okay, our space xj will be j times dx, and dx is our space increment. And j goes from 0 to j max. And we also discretize time. Tn is n times dt. In all of the Jupyter notebooks and simulations, you will more or less always find something like a dx and a dt corresponding to space-time discretization. So then let's use a very condensed notation with upper and lower indices. Upper index is always time. So for example, a time step n plus 1 times dt would be upper index n plus 1, and space xj would be denoted with p sub j. Okay, so xjtn would be jn and so forth. So that's a nice way of condensing the notation, not more than that. And with this, we can now use, and I think all of you know that, use the definitions of a second derivative in time and space. So it's always, you know, p by x or t plus 1 minus 2 times p of t plus p of t minus dt. And written here is n plus 1 n minus 1 divided by dt square. and equivalently for the space derivative. Note here also we discretize the velocity field. This is now Cj. And we also discretize, of course, the source field. And for the one-dimensional equation, that's easy to write this down in a space-time diagram, and that's called a stencil. That's another technical term. This is a space-time finite difference stencil or finite difference operator. So you see here, time is to the vertical direction, space is to the right. So you have j, j plus 1, j minus 1, j minus 2, j plus 2. So you can now basically identify, okay, this is Pij, this would be sitting here right in the middle. Okay, so what you see here is you have terms or elements here that are defined at different times in different points in time. So n minus 1, if you want, is the past. So this is n times dt minus 1, n times dt minus 1 times dt. N would be the level of the presence here, and n plus 1 would be the future. So often in my calls, I call this n, for example, here, this level I would call p. Pn minus 1 I would call p old, and n plus 1 I would call p new. And you can see that we have only one, and that's very lucky. We have only one value that lives in the future. And that basically, another technical term, that's called an explicit scheme, because we can explicitly write the future as a function of everything we know at the present time and in the past. That's not necessarily the case. With different finite difference approximations, you can get so-called implicit schemes, in which case, for example, here, you may have other values defined in the future that you do not know, and then it's called an implicit scheme. But that's very handy, because now we can, you can imagine, we extract the Pn plus 1, so we just simply multiply by dt squared on the other side, and put plus 2Pn and j and so forth on the other side, and we have our first finite difference algorithm. And I have in the exercise a more simple equation, the Advection equation. And it's fun, if you haven't done it, just to do it once to try and apply this and come up with your own algorithm. So in the end, you can see here, we extrapolate. That's another technical term now. This is an extrapolation scheme, because we are taking the left-hand side of the wave equation here, and this is an extrapolation problem. And if you want, on the right-hand side, that's a general interpolation problem. A derivative is nothing else but, in general, an interpolation problem. And again, that's something very general. And it's an important point here that I make for all the problems that come. The time-dependent part on the left-hand side, I always put on the left, is an extrapolation problem that's always solved basically with a finite difference scheme. All the methods from finite difference, pseudospectral, up to discontinuous Galerkin, they differ primarily in this right-hand side part, in the spatial part, in the way the space part is discretized. And that's very important, basically, to have a general view on all these different methodologies. Okay, so this is our algorithm, and you can now think how this works in practice. We can start by t equals 0. We can basically, everything is at rest, and then you inject a source, for example, and this would be then a pressure or an explosion source at a specific point, a specific grid point, as we go along, and then the algorithm or the space basically feels this this injected source and communicates it via the space derivative and extrapolates it in time via the time derivative. Okay, that's the math, and the beauty is such an algorithm, you know, can be written in a few lines. So as I said, P nu would be this basically n+1 in time. P is n, and P old is in time n-1. So basically, what you see here on this line, P nu equals to whatever. That's simply exactly this algorithm here, and the only you see 2 times P minus P old, 2 times P minus P old, and dt square. Sorry, the dt square we put is here. Dt square times the second time derivative, d2p here. And this second time derivative is, as you can see, is p plus 1, I plus 1 minus 2i plus I minus 1 divided by dx squared. And that's it. And then you extrapolate, and you actually add at each time step, you add, this is the index, p is a vector in space, and at index I source, at one point, I just upgrade basically the source time function here. And then at the end, you remap P old and P, because the next time, of course, the current P old is gone, and the new P is the current P old, and so forth. So this is a little bit of gymnastics. You have to think about it, but that's all. So you will see this in the notebooks. You can iterate for IT. In range NT, you start with 0 and you go until the maximum number of time steps that will always be NT. So if you do that and you inject, let's say, as a source time function, the first derivative of a Gaussian in one dimension I mentioned, you will end up with a Gaussian shape waveform. Now, I'm showing this here, for example, this is a snapshot in space after 51 time step, after 100, 150, 200, and 240 time steps. And with a certain setup, not important now. But what we know from the analytic solution, well, in theory, it tells us we should have a Gaussian waveform forever and ever and ever. This is not what we see. Something happens here. You see that? So basically the waveform disintegrates. Why is that? Now, there's another observation, and I want you to try this out. Increase the time step of the simulations in the notebooks, and suddenly you see, okay, at first maybe that propagates, but suddenly things start to oscillate and go to infinity. So the whole thing explodes. Yes? And well, the reason for that, and I'd love to do this in theory, but that would take too much time. But I encourage you to go to the Coursera course and go once through the not very difficult derivation of the so-called Courant-Friedrich-Lewy criterion. You basically just go into the finite difference algorithm with this kind of plane wave formula. That's e to the ikx minus omega t. You just replace t and x by jdx and ndt. And then you can basically find, you know, solutions for this equation. And what you find is, well, I get solutions, but only if c times dt by dx is smaller than epsilon, and in the 1D case, it's actually 1. And that's the so-called Cfl criterion. And if you look at this carefully, c is a velocity, and dt by dx is an inverse velocity. If you want, that's a, you know, call it a grid velocity. And it's, you know, try to make your simulation explode, and so then you hit exactly this mathematical boundaries. And again, the beauty with the finite difference method is you can calculate and predict that theoretically. You cannot do that, to my knowledge, you cannot do that with a finite or spectral element method. You basically have to investigate this numerically. Now, the other thing that happens when you do this mathematically, suddenly the velocity of the propagating wave becomes dispersive. In theory, as you may know, you should know, is in infinite full space, the wave equation, the solution, propagates non-dispersively. All frequency propagate at the same velocity, which is why this goes back to the original Green's function, which was a delta in 3D. That delta function remains undisturbed, and that can only be if all frequencies propagate at the same velocity. In our numerical world, this no longer is the case. And that's expressed in this bottom graph here to the left. So in terms of you have basically you have a wave number or wavelength axis. So you can translate it as number of grid points per wavelength. And basically, in a full space, the theoretical wave speed would be 2000. And the actual wave speed at a certain, for different Cfl criteria, that's doesn't matter here. If epsilon is 0.9, let's say, suddenly you can see that if the number of grid points gets less and less, or in other words, the frequency gets higher and higher, the velocity goes down. Okay, so this is exactly what we see here. So this is the expected arrival time, but some of the energy actually, even and it's the higher frequencies, they arrive earlier, actually later. I'm sorry, they arrive later. So the source propagates to the right, and that's exactly that effect. They have a smaller velocity, so they arrive later, and that's dispersion. That's numerical dispersion. And again, beauty of this simple finite difference schemes, you can derive that analytically. Very powerful, and that's called by the way, it's called the von Neumann analysis after John von Neumann, famous mathematician / physicist, one of the guys who invented the principle of computing. Okay. Now, if you do this in 2D, even I'll show the algorithm later, you also see interesting effects. So what you see to the left here is basically, a quarter of 4 different simulations. And to the left, this is what you would expect in theory. You should expect a beautiful isotropic wavefront. Now they increase, same algorithm. You can play this with this later. You increase the frequency. You decrease the number of grid points per wavelength. So you expect this to be less accurate. And suddenly you see something interesting. The propagation in vertical and horizontal direction looks different than in 45 degrees direction, right? You can see that. And you can, if you look carefully, you can see actually there's a lot of dispersion along the axis. There's less dispersion in 45 degree direction with respect to the coordinate axis. Now, again, very beautiful. That's something you can predict analytically if you go with this plane wave formulation into the wave equation. And that's plotted here. What you see on the right is the error of the phase velocity as a function of direction. And you can see, oh, theory predicts that the most accurate direction, independent of frequency, is 45 degrees. Think about it, whether that makes sense. Think about why this could be the case, and we can just discuss this later. It's quite weird, right? But you can see it here, right? This is entirely analytical. This is numerical. So you see that seems to be the case. Now, if you do this in 2 dimensions, not much more difficult. You have a time derivative. you have, again, still the velocities outside the bracket, and you have two space derivatives. And let's assume equal spacing, regular grid, and you can come up in the same way with an algorithm. The time extrapolation remains the same, so you add another index to the field, and that becomes a matrix. Before it was a vector, and if you're in 3D, it gets another dimension, and it's a three-dimensional matrix. But in principle, this is very simple, and here you get your values for the derivatives at P and JK. You get through these formula, and so let me walk you through a physical example. And here I want to spend a bit of time, because this is exactly the type of thinking that you will do when you will solve, when you first think, oh, that's a problem I would like to solve. Let's see what's the parameters that I need for my computations. And that's kind of independent also of the method. That will be very, very similar. So that's an image of a fault zone I took actually a few years ago, almost 20 years ago. That's the Landers in California. There was an earthquake. This is the fault line, so that's very close to the epicenter. And there's a shift of 4 meters or so that you would never see if you don't know it. But if you look from a distance, you can nicely see that horizontal shift. Now, we assume this is a vertical fault, crustal fault, that has usually a narrow, low velocity fault zone, damage zone with decreased velocities, and that's a very interesting situation to simulate, because we will see that there are trapped, something like trapped waves. Now let's try and set up this problem and see what kind of thinking we have to do before doing a simulation. So let's say we have we expect a 200-meter wide fault zone with a 25% velocity decrease in the center, okay? We expect our observations, or maybe with some observations in the field, they're between, well, dominant frequency 10 Hertz and a maximum frequency 30 Hertz. The velocities in the bedrock outside are 3,000 meters per second. We focus on shear waves, and the minimum velocity is 2,250. The extension we want to model is about 10 kilometers. So we reduce it to 2 dimensions here. So 10 kilometers wide, 10 kilometers deep. And the seismogram length should be 3.5 seconds. So that's the physical conditions that we would like to simulate. Now, the first question we ask, what's the smallest wavelength propagating in the medium? That is important because that will define the spatial increment dx, okay? So the answer, we have the maximum frequency. So here we need the maximum frequency, 30 Hertz. The smallest velocity is 2,250 meters. Then the shortest wavelength is lambda, is minimum velocity divided by maximum frequency is 75 meters. Okay, maybe check it, I hope it's correct. So how many numbers per smallest wavelength is required by the specific scheme? We can say, how many numbers per smallest wavelength is required by the numerical method, given the wave propagation distance that needs to be covered? How many wavelengths do we propagate? Remember the axis that I showed this morning. So the dominant wavelength in the medium is 225 meters. That's the minimum velocity divided by the maximum frequency. So we expect to propagate more than 20 wavelengths to the surface. And we use a 5-point operator. That's a little more accurate than a 3-point operator. We choose 20 points per dominant wavelength. And that means that we then have 7.5 points per smallest wavelength. Okay. So what is then the grid spacing that we need? With 20 points per dominant wavelength, we have a dx is lambda dominant divided by 11.25 meters grid spacing. Good. So next question. What's the size of the physical domain and how many overall grid points are required? We said we want 10 by 10 kilometers. So we have to divide 10 by 10 kilometers by 11.25 meters. So roughly it gets 1,000 by 1,000. So 10,000 by the x is around 900 grid points. So we have each field in space, pressure, velocity, will have 900 to the power of 2 grid points. Will the seismograms be influenced by artificial boundary reflections? Is it necessary to implement absorbing boundaries or increase the model size? So if you imagine we have a cube and we have a source in the center, then at some point we will get reflections from the artificial boundaries unless we do something about it, which is called absorbing boundaries. Here we say, well, with the model setup chosen, the fault source in the middle, we propagate up towards the surface. We will not expect problems with reflections from the boundaries. That's good news because absorbing boundary conditions is a nuisance. That's often not easy to do. So we do not need to discuss that. So what's the maximum velocity in the model and the resulting time step? We have the Cfl criterion, and the maximum velocity is 3,000 meters per second. We impose that. And let's assume a CFL value of 0.7, common value. Then we can use that CFL criterion to determine the time step. So dt would be epsilon times dx by c max. So we just take dt out of that equation. And that determines the time step to be 2.5 milliseconds. So the most important part of all this is the velocities, and the maximum frequency determines the space increment, and the maximum velocity here, and the CFL criterion determines the time increment. And well, we wanted a 3.2 long seismogram, so 3.5 seconds. Our physical unit divided by the time increment means we need to have 1,300 time steps. And finally, we can ask the question: how much memory do we need? Well, we just said that our basic elements is the 900 square numbers, grid points, bytes. So we will have, not sure. We have 8 bytes per number in a double precision world, like your 60. That's why your Windows version or whatever version is called 64-bit, because you have double precision numbers. That's 8 bytes. That means it's actually 900 squared times 8 bytes times 6, because I think that 6 comes from, you need 2 pressure fields at 3 different time levels. So you have here an overall memory requirement of something like 40 megabytes, which is really not a lot. You can do this on your smartphone today, so that's not a very challenging simulation. But of course, in more realistic cases, you need a lot more memories. memory. But I hope I made clear this kind of thinking is the first thing, back of the envelope, if you want, that you do before you plan a numerical simulation with whatever scheme that you use. And here's an example of a snapshot of such a. You can do this in the Jupyter notebooks. Very beautiful. You can learn a lot of physics of wave propagation with these simple 2D acoustic solvers. So you have these trapped waves here that are observed all around the world on fault zones, which 25 years ago was a hot topic. Today, it's well known that these kind of values exist. I stop here for a moment and ask, are there any questions to this? Because I think that's very important from a practical point of view.
Yeah, hi. Actually, there's just one thing I was always wondering about is why does one need absorbing boundaries? Like, I don't really understand why a model would produce reflections on its own.
Well, you know, you can try it out after, because let me just get you know, if you put a source here and you start to simulate, if you don't do anything, then, you know, once you get here, you will get the reflections. You will get the wave field reflecting back into the medium. And actually, to avoid this is tricky. In finite elements, you get the free surface for free, but you basically you never get an absorbing boundary for free. It is easy to implement with finite volumes because you work with fluxes. And with fluxes, it's pretty easy to actually define, okay, I have an outflux and I have no influx. But with finite differences, with discontinuous Galerkin, finite elements, you have to do something, and it's a whole own domain of numerical analysis to come up with efficient boundaries. The method of choice today is so-called PML. Partially matched, periodically matched layer. And it's complicated. It leads to instabilities. It's a tricky issue. Frankly, I try to stay away from absorbing boundaries all my life. But if you want to do efficient simulations, you have to deal with it. I hope that answers your question.
Right. So I suppose I could just increase my model size to like super huge, and then just don't care about the boundaries.
Exactly. You can
be inefficient.
Yeah. There are nice, simple ways, and I'll just show you one amazing trick. Maybe you've all heard of reflection coefficients that are proportional to impedances. Impedance is rho times VP, yeah? And reflection coefficients are proportional to the impedance. Now, what you can do is to come up with something like a taper. So let's say this is your physical domain. And I'm sorry, this will be ugly. And then you taper down the velocities at the end. So the velocity, oh, sorry, this is the velocities are going to zero. And at the same time, basically to avoid any reflections from the changing velocity, you increase density at the same time. And that means your impedance is always constant, so you don't get a reflection, and it's like your waves are getting slower and slower. So these are very nice and simple tricks that do not work as efficiently as the PML boundaries, but if you increase the model accordingly, that's kind of it's often sufficient. Okay. But there is a reason why I avoided talking about absorbing boundaries in my book because it's a nuisance, and you can write a whole book about absorbing boundaries. Okay. Any other questions at the moment? Yes, Jack.
I have two general questions about finite difference, but maybe if we're talking about the specific, we finish this example.
Go ahead.
Okay, my first question was, have people experimented with any success with using the method of lines for finite difference, where you just leave the time domain as a ODE with the discretization done only in the spatial domain, and then use some kind of like ODE solver package to solve the time domain rather than explicitly stepping?
I'm not sure what you mean by the method of line. Maybe that's an implicit scheme. Yes, people have done that. I'm not sure whether. So there's a lot of improvements you can do to this, very basic algorithm. So first of all, you can increase the length of the operator if you go further away, and you use not 3 points but maybe 5 points or 7 points. That's one thing. And you can also use Runge-Kutta type of methods or to improve the time extrapolation. I'm not sure whether that's precisely your question, but there's a lot of improvements you can do to this scheme, and all this has been done.
Yeah, okay. I'll move on to my second question. The other thing was with the numerical anisotropy, is it possible to redefine the problem as the product of an analytical solution for a homogeneous medium multiplied by some perturbation to get rid of the grid effects causing numerical anisotropy? That's something you can do with the iconal equation to remove anisotropy in the iconal equation, but I don't know with the wave equation you can do that.
I can't answer. If you will not get away, if you solve numerically things on a regular grid, that's it's a cubic grid, and that's anisotropic. So whatever you do, it's like you operate on crystals. You will not get away from this anisotropic property. The only, as you may know, it's a very interesting point, the only isotropic grid that exists in 2D is a hexagonal structure. And we played around with this. It's beautiful. You have an isotropic error. And the interesting, from a physics point of view, such an isotropic grid does not exist in 3 dimensions. That's very interesting. It does not exist. It does not exist in 3 dimensions. In 2 dimensions, you have it. It's called a minimal grid. And if whoever is interested, I can give details. But in 3D, there is no isotropic grid. You can use a random grid, then your error smooths out to be isotropic. But of course, that's mathematically not efficient. So you can't really get rid, in 3D, you can't really get rid of numerical anisotropy. Okay? Now, because we're in elasticity, I need to introduce also this aspect of the velocity stress formulation. I mentioned this before. Just replace the ground displacement by the ground velocity v. And this is the stress-strain relationship. And then you can, as mentioned before, you can redefine the wave equation in this form. So this is this slide you've seen before. Now, something very interesting happens here. In the original wave equation, in the original second-order wave equation, you had a space derivative of something that involves the material parameter, mu. In this first-order formulation, there is no, in principle, there's no direct derivative operating on mu. And that's an advantage, you could say, okay? And that's why a lot of so this is a coupled system with this solution vector, and many of the first finite difference algorithms, like also they form from Fourier, basically use this kind of velocity stress formulation rather than the displacement stress formulation. For example, the DG method that I defined at the very end is also entirely based on the on this formulation. So something now, don't be afraid. Something very interesting can be done when you solve such an equation. And this is called, and that's why another technical term is called a staggered grid. And that's very classic in finite difference type problems. And I don't want to confuse you, but I just, I don't expect that you understand these equations that are shown here, but just bear with me for a moment. What you see at the top here is basically a finite difference approximation of the first of these equations. Okay, that's the first line here. So it's a density. I put density on the other side. So you have here, I have a finite difference approximation of the first derivative of velocity. And the only thing I do is I just define these at j plus 1/2 minus j minus 1/2 divided by t. So the top, the superscript is time again. So at point I can define this derivative, this first derivative with increment dt, and I'm looking at the values at j, basically half a time step in the future and half a time step in the past. And I can do the same in space. So rather than looking, let's say, 2 grid points away, or 1 grid point away, 1 grid point away this direction, I'm looking at half a grid point away. Okay, so the grid imprint is dx. Now, if we look at this, it's maybe easier to look at this in this graph here to the left. So again, to the top is time, and to the right is space. And the point is that if you take a space derivative, for example, here between these 2 points, and the time derivative between these 2 points, you end up with something that lives at the same point in space-time. And that's called grid staggering. And the nice thing, and I'm leave it at that, we could go through all the algorithm, but takes time. The nice thing is you come up with an entirely consistent scheme where the values themselves are defined here and the derivatives are defined in between, and they always live there. And that means, for example, the density may be defined at a different location than the shear modulus. That's very bizarre, but it is consistent in the sense that we never need the density at point I plus 1/2. We always just need it at the points I, and the shear modulus we always need at in between values, I plus 1/2, I minus 1/2, and so forth. Why do we do that? Well, we gain in accuracy, because instead of using a fully centered scheme where you divide by 2 dt or 2 dx, we basically, by a clever arranging of the grid point locations, we basically decrease by a factor of 2, and that's of course a substantial increase in accuracy, right? Or in other words, a saving in memory. Okay, and I want to leave it at that, and in 2D again, this also works in 2 dimensions. You will have all Vx, V, Z, sigma, ZZ, sigma, XZ, mu, and so forth defined at different points in space, and it takes a bit of mental gymnastics to get the algorithms right. suddenly you have a forward difference and a backward difference operation, but it's entirely consistent, at least in isotropic media. And if you download some community code, it is most likely to have also in 3D such a grid staggering. You will probably never see this in the algorithm because in the algorithm I can I'm not sure I have a piece of code. You would not see that, but you would have to be very careful where your values are defined. So, for example, to output then velocities, you have to be aware that ux, uz, and uy are actually defined at different spatial locations, half a grid point apart. And if you want to be really precise, if you want to match an analytical solution, you have to interpolate. That's possible, but you just have to be aware that the fields are defined at different locations. Okay, so that's just relatively in a qualitative way. Is grid staggering is efficient. It's used in many circumstances. In all the community codes, you will have a staggered grid timer formulation. Okay, now any questions to this? Any questions to this staggered grid thing? It's just maybe a little bizarre, but you would have to sit down and look at this in more detail.
I got a question, sorry. I don't know if I understood it correctly, but so then basically like a good advantage of that would be like, since points in time and points in space are kind of like shifted, then one of the points serves like as interpolation for the other points because it's like in the middle instead of.
Good point. What you're saying, you're asking whether this is interpolation. Yes, it's the same as if we would do an interpolation, but the differentiation is just a first order interpolation. It's you know, whether you do an interpolation or a derivative, it's always a weighted sum over values known at some points. It's a very general way. I could, you know, if you want, let me try to write this down, and I hope I make myself clear. So where's my here? So if you want, whatever we do, we could say the nth derivative. The nth derivative of a function that's described on a on a vector would be a sum over, you know, I equals let's say 1 to n is, let me call these weights I by u I, or u by let's say u by xi. So what that means is, and here the weights would depend on the order of the derivative. If n equals 0, you have an interpolation. If n equals 1, you have differential weights. If n equals 2, you have differential weights for the second derivative. So the point I want to make on the right-hand side, we always do some kind of an interpolation. And, you know, it doesn't matter which points you use, but there's, of course, a minimal number of points you can use. And that's what's leading to this staggered grid formulation. I hope I answered your question.
Yes. I mean, with the writing of the equation, it was even more clear.
Okay.
With the weights. Thank you.
Any other questions concerning grid staggering? Okay, I'm looking at the time. Is it correct that we have already covered 1.5 hours again since we begin, right? So my suggestion is we take half an hour break and start again 3:15 for the last hour and see how far we get. Okay, so breathe out, get a drink, coffee, get some fresh air, and we meet again 3:15. Okay, see you.
Okay, thank you.
So welcome back. Few more seconds until the breakout sessions have fully stopped. Okay, so let's wrap up and let me ask you, do you have any questions that we could discuss here regarding the exercise sheet? Did it work? Could you play around with the Jupyter notebooks, or I had problems at the moment with my binder?
We had some problems, but as long as one person was able to get it going, so it worked okay.
Excellent. So any things you want to discuss? You know, it's a long day. It's a lot of material. It's tiring. You can also continue to, you know, if you're willing, continue to play around when it works, and we can discuss tomorrow any questions that come up. I do encourage you to try and understand at least the extrapolation part of the wave simulation algorithms, and you know, so that you understand the mapping between the mathematics and what's happening in a Python script. I think that's the most important part. Silence. Okay, has been a long day. So once again, any questions? Is everything clear?
The thing that we discussed.
Yeah, maybe just about that whole 45-degree story.
Ah, okay.
I was wondering if the grid doesn't have the same spacing for the dx and dy, is it still going to be 45 degrees, or is it going to be along the diagonal of one of the?
Gonna be equivalent. It will change, of course. The direction will change. It's an interesting thing to try out. I'm not sure it should be, whether it's easy in the Jupyter notebook in 2-dimension, whether it's allowed to change dx and dz. You could try. It's a challenge. And then you would, I guess you would see that it should no longer be in 45 degrees direction. That's my prediction. It will rotate. Any other questions? Okay, has been a long day. Thanks for staying on for so long. We start at 9 a.m. tomorrow, and take it from there. We'll go through finite elements and then the other 3 methods. And then we also talk about community codes and other things, and that will be followed by AxiSem in the afternoon. Okay, have a wonderful evening. Digest what you've heard today. The material is there. And I'll see you tomorrow morning, bright and early, hopefully fully recovered. Okay? Bye-bye. Thank you.
Bye. Thank you. Thank you.
Hello, everyone. Are you back? Excellent. Thank you. Okay. Now, last leg for today. What I plan to do is we'll have a few more slides. I guess you see my slides. Can I have a thumbs up in presentation mode? I skipped a few slides, don't worry. I'll do a few slides on the Pseudospectrum method, and then we look at the exercises. Okay, we're still talking about the finite difference method. And what I want to end up with is everything we look at is basically in Cartesian coordinate systems, X, Y, Z. So you could also ask the question, well, what about if we want to do global wave propagation, which was actually something I started as a postdoc. Can we solve wave equations also in other coordinate systems, like cylindrical coordinate systems and or spherical coordinate system? Actually, if you look at the literature, one of the first, really historical, one of the first implementations of a finite difference scheme was for global wave propagation using cylindrical, in 2 dimensions using cylindrical coordinates. This was in the late 60s by an Israeli scientist. So in principle, that's possible. That's just something I would like to state. What you see here, bottom left, this is a discretization in spherical coordinates in axisymmetric media. So you assume basically independence in phi. So if you see me turning around, this would be the phi direction. I just have basically a section from North Pole to South Pole. And this is, in fact, a staggered grid, which just talked about staggered grids in an elastic notation. And I want to say it basically works. It doesn't work well in 3D because you have problems with the singularities in the wave equation in spherical coordinates at theta equals 0. So if you stay away from that for spherical sections, that's possible. and axisymmetric media is also possible. This is actually something very similar to what's happening in Axisem. So my previous student, Tarje, he continued to work on this as a PhD student using spectral elements. So message here is simply, yes, it works. You can see here, this is almost, well, this is more than 25 years ago, mid-90s, one of the first snapshots of global wave propagation at the time using such an algorithm. Okay, this is SH motion in the mantle on the right. It's a real through the Prem model, a spherically symmetric model. But here, of course, you can also inject sort of lateral heterogeneities with some restrictions. Okay, so the only message here is finite differences can, in principle, also be applied in other coordinate systems. So to sum up, the FD part, we replace the partial derivatives by finite differences and can, by doing so, solve partial differential equations for arbitrarily heterogeneous media, in principle. The resulting space-time discretization leads to unphysical phenomena such as numerical dispersion that can be avoided by sampling with enough number of grid points per wavelength. Again, the terminology here is important. You can improve the accuracy by these finite difference operators by using, we didn't talk about this, but you can remember the 3-point operator can be extended to 5 points, to 7 points, and so forth. And by this, getting more accurate. We developed the Cauchy-Friedrich-Levy Cfl criterion. That's a stability criterion. It restricts the choice of the space-time discretization. In higher dimensions, meaning 2 and 3 dimension, the wave propagation becomes anisotropic numerically. This has to be avoided. And also the implementation of boundary conditions needs special care with finite differences. We didn't talk about this in general. Now, you can see this point here again, the third point, the accuracy can be improved by using information from more grid points. This becomes an issue now when we talk about another method, meaning the Pseudospectral Method. Before I go to that, I say again that finite differences is the method of choice for flat surfaces and body wave problems, particular exploration. I mentioned this before. Something I skipped is there are very accurate operators, but they're not very widely used. There are new approaches like summation by parts that are better for topography. There's an interesting combination. I mentioned this with homogenization. And there's also community codes. We'll talk about this also tomorrow, like SW4 and SOFI 3D from University of Karlsruhe. But we'll get back to this. Now, historically, and this goes back to the late 70s, early 80s, the question was, how can we improve the accuracy of the spatial derivative, the space derivative? Now, in the early days of computing, let's say 40 years ago, memory, RAM, memory was expensive. So anything that is more accurate in the spatial discretization and the space derivative reduces memory. So this was, from a mathematical point of view, the goal. How can I use less points per wavelength from a mathematical point of view? And that question led to the Pseudospectral Method. And I say it from the beginning, I think it's the most beautiful method of all. Very simple, but it's never used today. And I'll try to explain why. So in a nutshell, again, here's our snapshot for a one-dimensional pressure wave field. We've seen this before. Now, the principle of the Pseudospectral Method is very simple. You take this space-dependent field and do a Fourier transform, a spatial Fourier transform. that gives you the spectrum of this, and this is not an artistic view. This is this here is the spectrum of this field. So you have, this is the amplitude spectrum. Of course, the spectrum is complex, has phase as well. Now, what you see here, this dashed line, is actually the function ik. I is the imaginary unit, so it's basically just a straight line. Now, as should be clear later, the derivative operation in the frequency and the wave number domain is simply a multiplication of the spectrum by ik and an inverse transform back into the space domain. Okay, so FFT is what we do in the computer on a vector. FFT gets you the complex spectrum. You multiply that spectrum with ik in the spectral domain, and you do an inverse transform back to the space domain to have, and now this is important, an exact derivative. That's the key word here. On a regular grid, you have an exact derivative where the error is only machine precision error. Wow. We will think later what's the price of this. So this is much less dispersive because there's no dispersion in space. It also has no numerical anisotropy, very important. However, boundary conditions are very hard to implement. And even worse, it's a global communication scheme. What that means, let me try to explain maybe just even here what that means in terms of, because it's so important, that's the reason why it's not used today. What does that mean, this global communication? It means, look at bottom left. If I have a point here, if I want to calculate the derivative at this point, it depends on the entire domain. So the derivative calculation for this point here depends on all points from here to there. It's a global communication. It's like a convolution. Okay? Remember, in the finite difference method, let's say the influence domain was very local. Now the influence domain is global. And that means, from a parallelization point of view, very inefficient. And that's basically the reason why it's not used today. Okay, so...
Heiner?
Yes.
Does that suggest, though, that if you, like these days, you can have nodes with like huge amounts of shared memory, you know, like 200 gigabytes of shared memory per node. So could it be possible to do, you know, like 10, you know, you said 10 seconds was 256 gigabytes. So you could maybe have 10-second full simulations using the pseudospectral method without actually having to do any real parallelization now, right?
Yeah, excellent comment, Jack. So yes, if you have a machine and a shared, maybe some of you don't know this, but a shared memory machine is a machine where basically inside that node, you have no, you know, you're not penalized for long communication distances. And that's true. That can be done if you can fit a pseudospectral scheme into one of such a large shared memory node. Then you can have a very efficient
recording in progress.
Method. Oh, thank you. Yes, I forgot to start the recording. So absolutely, the answer is yes. And I should say, I developed some pseudospectral methods when I was a postdoc in Cambridge, when we had a shared memory machine from DEC Alpha. DEC Alpha no longer exists today, but so we tried to make use of this, you know, of the machine architecture at the time. Of course, GPU is not in the direction of shared memory. Okay. So let's go a little bit in more detail. So stop the commenting here. So I guess most of you have seen the Fourier transform. So this here is the forward transform. The forward transform is you take a vector, a field f of x, so this is analytical here, and you apply this transform and you obtain a spectrum, an imaginary spectrum f of k that has a real part and an imaginary part. And the inverse transform is the inverse transformation. I use this funny f as an indicator of the Fourier transform. Gets you back to space. Now, the question you can ask is what happens, just take that equation and take the space derivative. Okay? It's a little more complicated than it's shown here in the sense that you have to get rid of a antiderivative, but that's part of the condition that the field goes to 0 towards infinity. And then you can write it like this. So the Fourier transform of the derivative is the derivative of this whole term. And so if you take the derivative here, you get this ik in front of the classic transform. That's exactly the ik we saw before. Now, let's just call this capital D of k. Capital here stands for everything that lives in the wave number domain. And so you see here that suddenly you basically have a filter operation if you want, because you have a spectrum and you multiply the spectrum with something which in the space domain is a convolution theorem. Okay, that would be also a nice thing to further discuss. But let's keep it at that for the moment. So let's just say we can basically calculate the spectrum of the nth derivative of the spectrum of f of x, which is capital F of k, by simply having ik to the power of n. I hope that's clear. So this is in the continuous domain, and this is what I just said. So then the nth derivative of a function f of x is simply, you calculate the forward transform, multiply ik to the power of n, and do the inverse transform. Okay, so the funny f here, of course, in an algorithm is just FFT of a vector. Now, how does this apply to, let's say, the now very well-known acoustic wave equation? Well, the left-hand side, as I said several times before, remains a finite difference approximation in general. So the only thing that you want to replace with a pseudospectral scheme is this operation here, the second derivative of P. Okay, now how does this work? Well, the second derivative of P is simply, the inverse transform funny f of ik square times the Fourier transform of P. Okay, and actually here's the algorithm for that. It's very, very easy. So a Fourier derivative here, the second derivative Fourier, this is in Python, is actually just the FFT of f times ik, so I here is 1j, times k square, you times the FFT of f. So that gives you this part here, right? And then you take ff and do the inverse Fourier inverse transform. Okay, and you have df, which is on a regular grid. So f is a vector, ff is a complex vector. The IFFT of ff again is a complex vector, but the real part is the derivative of f defined on the same grid, on a regular grid. It's exact up to machine precision, and isn't that fantastic? It's very, very simple. The only thing I hear ... here stands for you have to initialize k. This is the only thing that's a little tricky. But once you initialize the k, this is just the k vector. K is a vector here. It's just the axis in the spectral domain. That's all. And so again, you now know this kind of algorithm. We have again the extrapolation scheme to the next level. So all these are vectors. It's exactly the same as the finite difference scheme. And the only difference is I'm calling here this subroutine or function Fourier derivative, the second Fourier derivative. You get it out of here, and that's it. And it's, of course, a lot more accurate than the finite difference approximation. But what is the price? Well, the price is on the same number of grid points, let's say 1,000 grid points. Each derivative calculation for, if you want, for 1 point involves floating point operations of 1,000 points and not only 3 points. So it's computationally a lot more expensive, but I can live with a much smaller spatial grid in the global domain because the derivative is much more accurate. Okay, so here is, let's say, a pictorial description, and on the left, probably you've seen this discrete Fourier series. What I show here is just a discrete Fourier representation. The function is x squared, and you see the dashed line is x squared function between 0 and pi, let's say, and you replace it with a discrete Fourier series that is exactly interpolating at the grid points. So that's this exact interpolation property. If you zoom in, you see that at those points, the solution is exact. That doesn't mean in between it's exact, not at all. You can see that there's this overshoot, Gibbs phenomenon, and so forth. Okay, but this is this fantastic property. Now, on the right-hand side, let me explain what you see here. You see here, let's say, a simulation. This is a snapshot in space of a finite difference simulation with a 3-point operator after 21, 43, or 64 wavelengths propagation distance. The analytical solution is this here, top right. That's what you expect. And you see the finite difference solution is this, everything is the same. dx, dt, everything is the same. And so the finite difference solution with 3 points is totally screwed up. It's wrong. With 5 points, it's already much better. It's closer to the actual solution that we expect. But also after further propagation distance, it's very dispersive. And the Fourier method is spot on, let's say, after 21. And you see that it's much less dispersive because the error only comes from the time integration. Okay? There's no error in space. Wow, that's really amazing. However, I have to always say warning if you look at this figure. It's a very powerful message, but it by no means I want to say here that finite difference is bad. Not at all. Because this code was much faster. This is a lot faster, and this takes a lot more time. But it basically means for the same memory requirement and more floating point operations, and that was very relevant 30 years ago, I can get a much more accurate solution. Okay? So I say this again because I don't want this to be misunderstood. You can make a very, very good finite difference solution. Simply, you need more grid points per wavelength to make it accurate here. Here, I just want to compare everything. Everything is the same, but you see the impact of the accuracy of the spatial operator to calculate the derivative. Okay? Any questions? I hope it's clear what I'm saying here. Okay, now another cool thing is what I already mentioned. This is a picture showing again exactly the same setup in 2 dimensions with a finite difference method and the Fourier method. And you see that the finite difference method is very anisotropic. We have an error that's anisotropic. And the Fourier method is not anisotropic. There is no numerical anisotropy. And that's a very nice property. For example, if you want to study physical anisotropy, this is why late 80s, early 90s, people jumped at this method to actually study wave propagation in 3D anisotropic media. Because there you are sure that you do not, there is no confusion because numerical anisotropy and physical anisotropy. So very powerful. Now, finally, just a few more things. If you have the elastic wave equation, something like this, you simply replace the left-hand side with a second derivative approximation using finite differences. And then you have the new situation that you have first derivatives on the right-hand side. And also those, this is kind of a workflow, can be calculated using the Fourier transform. You start with a vector ui at time j, take a fast Fourier transform, then you get the spectrum. You multiply not with k squared, but with minus ik. You get the spectrum of the first derivative, do an inverse transform, and you have an exact derivative of u, and so forth. I think that's fairly straightforward. So you can do it in exactly the same way using the elastic wave equation in 1D or in 3D for that matter. Okay. Finally, again, I said not many people are using that today. A few people like Furumura, he worked with Brian Kennett, used it for wave simulations, for example, for the moon in spherical coordinates. You can also combine it with finite differences, so you won't only have pseudospectra in 1 dimension, so it fits into one, like a shared memory node, and then again can lead to a fairly accurate and efficient scheme on parallel computers. But to be honest, today I don't know of anyone using that for actual research applications, except for old legacy code. Okay, now yeah, let me stop here. We can discuss the questions later. Let me stop here at the end of the pseudospectrum method and first ask you any questions concerning that part. It's getting late, it's afternoon. Okay, so I suggest the following. We have, I don't want to overstretch you. Let's take another half an hour up to 4:15 to look at the exercise sheets. And so that's the second one. Let me bring this up. In breakout sessions. And so there's a couple of general questions. Again, I'm sorry this is not so well resolved. So talk a little bit about these comprehensive questions. And if you want, also try to solve this. Doesn't take much longer than a few minutes. There are 2 theoretical exercises to show the accuracy of this finite difference approximation using Taylor series. And you can also take this very simple partial differential equation, the Advection equation, and come up with an extrapolation scheme, as we did for the wave equation. And apart from that, there's my choice would be look at the simple first derivative calculations. You can extend that to the 5-point operator. There's an exercise there, and also the AC1D, which may take a little more time. But of course, you can also do this after we're finished. and then run any of the, not the finite element, run any of the FT or pseudospectral approaches, and play around with the parameters. And again, I think a nice way of doing this is if maybe one of the groups is sharing the screen, and you discuss what happens in the code. Of course, let's see how far we get in half an hour. My suggestion would be I'll let you now play around with this for half an hour, and then we do a final discussion at Okay, shall we start? The bell is ringing. Good morning, everyone. Hope you had a good evening and night. Good to see you. Let me, to warm up our minds, we're talking about wave propagation, we're talking about numerical methods. And yesterday we started with two methods. We looked at the finite difference method. Historically, that was one of the first to be applied to wave propagation. And the question of improving the accuracy of the space derivatives basically led to the introduction of something that people called at the time transform methods or pseudospectral methods. By the way, I never explained the word pseudospectral. Or maybe does anyone have an idea why it's called pseudospectral, which is a very, very bizarre kind of wording? Any idea? Pseudo basically says it's it's something like, but it's not really. So the reason is we're not solving the partial differential equation in the spectral domain. But we're going in the spectral domain to calculate a derivative, and then we go back to the space-time domain. That's why it's called pseudospectral. It's not really a spectral method like normal mode free oscillation calculations. That's the reason. Okay, so we made some advances in the sense that our spatial derivative, our spatial interpolation derivative operations were a lot better exact to machine precision. However, the price was very high. The price was high in terms of number of floating point operations, and also remember this kind of global communication scheme that we have, like in a matrix inversion or a convolution type of operation, very expensive. Okay, so this is the state where we are today, and we're entering quite a different world now. I will present you now the finite element method, and the finite element method is something that was, I think, started in the maybe 30s, 40s already of the last century, in particular in structural engineering, in trying to understand vibrations or properties of buildings, and analyzing the stiffness and strength and stresses in structures. And actually that has an impact on the naming, for example, on the matrices. Then you will see that later. It is interesting, and let me say this from the beginning, it is interesting that the classic finite element method, and by classic I mean using linear basis functions, you will understand that in a minute, has not really been used in seismology. That's very interesting. And when I was preparing this book, I was trying to talk to people who were in that field. Jakob Bielak is one big name, and because I had the impression the reason is that it's actually a lot more complicated than finite differences, at least from a derivation point of view and so forth. And he totally confirmed that it's correct, even though it has some advantages in quotation. people didn't really use it because it's just a lot more involved, complicated to implement. But what is very important, many of you probably are going to use the spectral element method, SpecFem or Salvus or Rexem or other flavors of the spectral element method. And I think really it's enough to understand the very basic linear finite element method plus a little more to sort of understand what's happening inside. So I'm expressing a warning. If you have never seen this before, that's a little hard to digest if you see this at the very beginning. But let's try at least to go through the basic mathematics, the derivation. It's a very different kind of philosophy to develop a numerical solution system. And it's good to at least try and go through this derivation once. Okay, so I'll share my screen. I guess we're now almost complete. So let me get in presentation mode. Okay, does that work?
Yep. Yes.
Yeah. Okay, so let's get started. Finite element method. As I always do, I'll give you sort of the finite element method in a nutshell. We have again let's say a sample. Really, this is a real simulation, a one-dimensional simulation of a finite element scheme, and you see this gray shaded, so that these are different velocities, so it's a heterogeneous model. And what is conceptually different now, and you can see this at the top, is we're basically dividing up the space not into grid points, but we're dividing the space up into elements. And so that means, and that's a fundamental difference, we will now have basically a continuous description of our wave field and not a description that's based, let's say, only on grid points. In the end, it really doesn't make a big difference, but it's a conceptual difference, okay? So what is between the vertical bars here is an element. And here, that's already, you can already see this is we describe the wave field in between. So this is let's say a zoom in, really in an actual zoom in here. And we describe the field with a linear function, and we have basically know the values, or we work with the values at the edges of the elements. Also note here, and that's a fundamental difference to the last method we're going to encounter today, both elements, the element boundaries share the same values. So that basically is a continuous Galerkin method, and it's not a discontinuous Galerkin method, as we will learn later. Some aspects, we will get to know something that's called the weak form of the wave equation. Wave field is interpolated with linear orthogonal basis functions. Also, it's a very important difference here. We never really work with the derivative of the wave field. We actually work with the interpolation of the wave field and derivatives of the so-called basis functions. Will become clearer later. What is also different, we will develop, in principle, always a large linear system of equations. You all know that you have certainly done that. And in principle, if we solve realistic problems, we have huge linear system of equations. Like let's say a matrix inversion, but that system matrix may be huge. It may be millions by millions. And
That's very hard to solve, and in a general way, that means you will have to involve basically all linear algebra tools, matrix inversion tools that are also, sometimes hard to implement or not very efficient on parallel supercomputers. Now, one aspect that I want, you should remember is, and I mentioned this before, something amazing happens. The free surface condition is implicitly fulfilled exactly. And that's a major advantage. This is, some of you work in Andreas Fichtner's group. I'll never forget, I gave Andreas, when he was a PhD student, a finite difference code with, spherical geometry to work on regional wave propagation. And he looked at the accuracy and he dropped it, and he started coding a spectral element method, because the free surface condition is implicitly fulfilled, is more exact, and you have a much higher accurate surface waves. So that's a major thing. Another important aspect of finite or spectral element methods as well, in principle, at least finite element methods work on hexahedral or tetrahedral meshes. We'll not talk much about meshing, but the geometrical flexibility of the finite element method is one of the main advantages. You can think of buildings, or if you think of engineering, airplane wings and so forth, and anything, or the vibrations of tools, or also in the car industry. That's the reason why the finite element method has been so popular in these areas. Okay, so what we do is we start with the simplest possible way, simplest possible equation to explain kind of the mathematical concepts. So in the end, we would like to, of course, solve our fancy one-dimensional equation, elastic wave field, shear motion. Remember, that's could be a guitar string motion, propagating in x direction. So that's you can do this in your sleep now. This is the one-dimensional wave equation. Now what we do is we're trying to start by solving the static case. Static case means the time derivative of the displacement is 0. So that's what's expressed here in this equation here. So we make another crude assumption that to make it really simple, that the shear modulus is constant. So think of a string. This would have a homogeneous properties, and then we have the equation here. It's a Poisson equation minus mu second derivative of in space of the displacement is F, and F is some forcing. And if you think of I could take a dark guitar here. If you think of a guitar string, it's like my finger here would be a force. I'm lifting it up, and with a certain force, and depending on mu, you would get a certain displacement, and that's what we're solving. So it's a fairly simple problem. Okay, so how do we do this with a finite element method? Now, sit back and relax and try and follow this reasoning. Now, what we do is, I'm going back, sorry. We take this equation. So this is the equation we want to solve. We're now doing something funny. We're say, okay, this is an equation that's defined in space. So now let's just multiply an arbitrary space-dependent function defined on the entire physical domain to this equation. Okay, and we start calling this V. That's it's called a test function. Okay, we can do that. We do not change the solution of that equation. In to some extent, it's not different than adding this equation, multiplying this equation by 2. We multiply it by an arbitrary test function that we define as v. Okay. Now the next step we do is we are integrating this both sides over the entire physical domain that is denoted as D. Again, this is a linear operation. We can do this without changing the solution of that equation. Okay, so here we go. That's this part. Now we are doing something. So you can see now we have the second derivative here. Now we're doing something with this left-hand side of that equation. We're doing integration by parts, and you all know this, I guess. The integration by parts is well, you have to define u, v, v, u prime, v prime, and so forth. And so you get, as you remember, you get one integral and one antiderivative. And this is already a very important point here. So you end up here with an equation with a first derivative of the displacement field, a first derivative of the test function, minus this antiderivative. And this antiderivative is evaluated at the edge of the domain, x min, x max. Okay. And here comes the main, one of the main things here. What's inside this square brackets is mu times the derivative of u, and that is the stress. Okay, so I could, I don't, you can see it here. This is that's the stress, and it's evaluated at the boundaries. And if we assume a free surface condition, we can actually scrap out this and term, and we have the free surface condition implicitly fulfilled. Again, one of the most important aspects here. I'm losing my mouse. I don't know why. Okay.
Heiner, can I ask something?
Yeah, sure.
So what does it mean to have a free surface condition for a one-dimensional string? Because then that string would not be attached to anything.
Well, it means good question. I think it's the free surface leads to a perfect reflection. Okay.
Oh, yes. Yeah.
Now, a perfect.
That's periodic.
Yeah. So I think it's an open end. That's like if you take a flute. Actually, it's also the boundary condition is an open end. So it's like the free surface can vibrate, but it has no stress.
Yeah, but that would be for the one end of the string, but the other end would still be fixed.
Well, if you have both free surface conditions, then both one would be free, but you would have a reflection. But in any case, you will get a perfectly reflecting boundary. Okay.
Okay.
So the next step we do is we're still entirely in the continuous world here. Okay, I'm losing my mouse. We're in the continuous world, and the next thing is we have to do, we replace the u by u bar, and u bar is now an approximation of u, and it's composed as a sum over weighted basis functions phi I. Okay, so basically we had something like this before in the pseudospectrum method, for example. The basis functions actually were cosine and sine functions. That's how we obtain the Fourier transform. Here we do not know, we do not specify the basis functions yet, but there you can see here also that we call these weights not W or C or something, we call them U. in what we call them U for a reason. The reason is that these basis functions are basically supporting only one value of the displacement at the element boundary. So the basis functions will have the value 1 at the element boundary and 0 everywhere else. That's something we call also a cardinal function. So basically, we can describe with like this. We can describe any function with giving or multiplying the basis function with the actual value of the function itself. And that's why it's a good strategy to call it actually U. So this is now the discrete U. Okay. Now with this U bar, we enter the weak form of the equation, of the wave equation, as we've seen here. Let's see whether I can. Oops. Oh, okay. Sorry. Just a sec. Okay. So we enter this equation here. So nothing magic. Okay, accept that. And we continue. Now, the first thing we asked, what do these basis functions phi I look like in the linear case? Well, let me first. They look like this. Very, very simple. So we have a domain from, this is x min, this is x max. We have actually 9 elements here. We have 10 element boundaries, and this is n minus 1 elements. And this would be the first. This would be phi 1. So it's 1 at this boundary and 0 everywhere else. This is phi 2. So it's 0 here, 1 here, and 0 at all other, and so forth. So I think you get the point here. And mathematically, this can be described in this way. And here, this is very general because, and that's something I didn't mention before. In the finite element method, you can change the element width very elegantly, basically per element, and that's called H adaptivity. H stands for the element width, and that's a very nice property. Let's say if you have a low velocity zone and you want to mesh this more finer in the finite element context, very easy to do. Finite difference, very difficult to do, or basically impossible in a regular way. So this is the mathematical description of this figure here, these functions. Okay. Again, interrupt me. I'd really like you to follow here. If I don't want to lose you. Ask any questions, please. Okay. So now comes another key point. So let me go back again. We're here, and we just enter the sum. We put this sum here as into U bar. Okay. And at the moment we have not said anything about V, what we do with a V. Now this is the trick. Of all Galerkin methods, Galerkin Principle. Galerkin was a Russian mathematician, 19th century. So what we do is we use as test function V, we actually use the same basis function as we use to describe our field. Okay. So we replace the V by the phi, give it another index J, and very easy to see if we go back to this graph here, it is obvious that you will have some kind of orthogonality property here. Okay, so these basis functions are orthogonal, which is of course a very nice property. And then, for example, if you you can imagine phi j, phi I has the delta property. So it's only 1 if I equals j, and 0 if I not equals j. Okay, so again, mathematically, no big deal. This is u, and we just have replaced now this function. But what we see now, this suddenly has a totally different structure. We're now in a discrete world, because we have n basis functions, and we sum here over n, and if you can see already this n is connected to the number of elements or basis functions, which is in this case equivalent. Now, all these are linear operations. What we can do is we can take the sum out of this integral, and now we will basically have a system of equations in n. So we have, if you want, j equations, and you can already see that we have matrices and vectors in this equation. So what's under this integral looks like a matrix. So we have a ij here, we have a ui here, and we have j on the right hand side. So basically we have j equations here, and we have a summation over I on the left hand side. Okay, I hope that's clear. Again, what are the unknowns? Make sure you understand what the unknowns are. The unknowns are ui. Mu is a property. We said it's constant, so we could also take it out of the integral. And phi i's are known. You know, phi i's are imposed basis functions. All this is known. The only other thing we impose, but we know it when we solve the problem, is f. Okay, so what we don't know, our unknowns, is u. Okay, what's next? Well, there's at the moment these phi i's and so far, they are all defined, or everything is defined on a, let's say, a global spatial scale, not global, but on the entire domain D. And another characteristic of everything you do in finite or spectral element type methods is you go to a local coordinate system. And so that means you define a new variable xi that's defined between, for example, 0 and 1. And so x minus xi means basically I is the left boundary of the element, and then xi is defined between 0 and 1, for example. In spectral elements, actually between -1 and 1. And h is the element size, okay? And so you can do, you can redefine your basis functions in this local coordinate system. That's just for you to know that later we'll see integrals over xi and not over x. And again, that's a very nice property and a nice specialty of the finite element method. You basically break down, all the calculations are done on an element rather than on the entire global scale. It also means in terms of parallelization, that is interesting. Okay, so that's a mapping to a reference element. And the derivatives, by the way, if you have this these description of the basis function, the derivatives are of course very easy. I'm going back to this. Of course, the derivative of this function is simply that you get a minus constant, and here you get a plus. This is a minus, this is a plus constant. So this makes sense. And actually the derivative is called 1 over h is the slope, and -1 over h is the slope if it's, it's going down. So all this is very simple in the linear case. And here's another description. This is another example of a basis function. So this is one basis function here, the triangular shape, and that's the one next to it in the next element. And the derivatives are here. This is positive 1, assuming h is 1, and negative next to it. And okay, so that's the geometry basically of these basis functions. Now let's build up the system description using matrices and vectors. So we introduce U as a vector. So remember we had this sum over U I phi I. So we now describe this U as a vector. So these U1, U2, Un, these are the values of the displacement field at the element boundaries. Okay. Now the source vector we keep, we actually keep the integral. So each element of the source vector is an integral over f psi 1 dx. Okay. And the integral that we've seen here, now the phi I containing phi I and phi j is called the stiffness matrix K, because it involves the stiffness mu, that in this case, and that's very special, we won't do this in the spectral element case. Here we'll take it out of the integral, and at the moment this is still, there's basically a dx missing, but this is indicating that's an integral over the entire domain. So Kij is the stiffness matrix. Okay, so capital K boldface means it's a matrix. Here's the mapping from, this is the global matrix, and if you describe it in the local coordinate system, in the element-wise element coordinate system, it gets a psi sub psi here, and it's an integration over psi. But so let's let me just give you an example. This of course you can do this later, but now to calculate these matrices in the linear elastic case is very, very simple. As you've seen, for example, a K11, this would be one element. It's the, you saw the derivative of these basis functions are very simple. It's -1 over h, -1 over h, and you can integrate this from 0 to h. So this is the end of the element. From 0 to h is the size of the element, and the result is mu over h. Okay. Another example, so this is a special case, was 1, 1, 2, 2 is a diagonal element. You get 2 mu over h. Okay, and an off-diagonal element here, for example, 1, 2, you get minus mu over h. And if you put it all together, your stiffness matrix has these entries: 1, -1, -1, 2, -1, and so forth. If I take out mu over h. Surprise, surprise. You've seen these numbers before. Let's say 1 minus 2, 1. Remember? What was that? That was the derivative operator for the second derivative. That's not a coincidence. So you can see already this would, if you want, multiply this with -1 and divide by h square. You have the matrix corresponding to the second derivative finite difference matrix operator. Okay, so you can see here already totally different derivation, some similarity to the finite difference method, and I mentioned this here in the last sentence. Okay, so we now know what this matrix K looks like, and we can basically pull things together. So let me go, close your eyes. I'm going back. You can see up here this equation Ui Kij Fj. With this definition we just said, that's simply this equation here, just exactly this equation here. So we have a vector u Kij and a vector Fj. Okay, close your eyes and we're back here. Okay, that's simply with the definition of the matrices here. So in bold matrix notation, KTU equals F, and our unknown is U, and so of course we need to put the KT minus 1 on the other side, and so that's our algorithm. U KT minus 1 F is, if you want, that's the solution of our system. Okay. Now, this is, let me see whether I have, no, I don't have the code, but I'll show you later, or you check it out in the Jupyter notebook. This is really after initialization. This is what will be done on the computer, and you can write it down in this one single line. So it's really very simple. Careful. I really have to state this. Here you have a banded matrix. We've seen it before. This is a banded matrix, and so it has a lot of zeros here. And I'm writing it in this way for a real problem. You would never do it like this, but for the sake of simplicity here and also in the codes, I always explicitly write it in this direct mathematical form. Okay, so that's from a computational point of view, that's not efficient, but it's it's the simplest way of writing this. Okay, so that is the solution. Now, a couple of more points. Again, one is that the beauty of finite elements, I mentioned this before, is you can just change the element width. It will modify the actual entries of the stiffness matrix, but that's all. It will, in this case, there was no time dependence, so there's no Cfl criterion, there's no problem. Okay, but that's a fantastic flexibility, which would be a lot more difficult to do with finite differences. Now, something I didn't mention is you can write the wave equation when you do it with finite differences in exactly the same way as a matrix vector in terms of matrix vector operations. If you do that, you get, I mentioned this before, you have a finite difference. This is the second derivative operator, pictorial for the finite difference method. And also you would end up with a mass matrix. I'll define that in a minute, which is basically just the density values here in the diagonal. And so in the finite element method, the K, at least in a pictorial, well, looks exactly the same. The stiffness matrix would correspond to this second derivative operator in the finite difference method. And the mass matrix, you will see it looks a little different. It's banded, it's not diagonal, but again, the structure looks very, very similar. Okay, now I hope I can stop here for a moment. So this has been the static case. Okay, that's the solution. We'll quickly look at the code later. So now I want to just make the step and go to the wave equation. Remember the wave equation. The only thing that has to be added here is the second derivative in time multiplying the density. Okay.
Heiner?
Yeah.
Maybe if I can come back to my question about the boundary conditions. So you showed us also the entries of the K matrix, which have like 1, -1, and -1, 1. So if I'm not mistaken, this matrix is singular. So why, how can you invert this?
It's not singular, you can invert that.
Okay, it's not rank n-1?
it's not singular. You can invert that matrix.
Okay. I'll check.
Otherwise, you yeah. Otherwise, the codes would explode. So that's invertible. Okay. Other questions?
Isn't it the case that we need to add a boundary condition? I mean, add at least one. What is that? Directly boundary conditions to make the matrix non-singular.
Yeah, I'm losing out. I missed out the boundary condition here. I dropped the boundary condition. What happens, and fortunately I don't have the graph here. The boundary condition basically leads to just an entry at the first and the last element of the force vector. So that's the way a boundary condition can be implemented here. So you add a value at the beginning and at the end of the force vector. Okay. That's yeah, I dropped that part. Okay, other questions? So let's continue with the 1D wave equation. So there is one more matrix that is being introduced, and that's the mass matrix. The mass matrix is called mass matrix because you have the density values here. So it's Mij, and it does not involve, like in the stiffness matrix, the derivatives of the basis function, but the basis functions themselves. Okay. And with this, you know, remember UK equals F was the static problem, and what's now added is U double dot, which is the derivative of U times M. And you can rewrite that with transposes, and transpose U double dot plus KTU equals F. Now, what happens is you can now, as I mentioned always several times, the time-dependent part is always done with a simple finite difference approximation or some higher order finite difference approximation. So here we simply replace U double dot by U t plus dt minus tu plus ut minus dt divided by dt square, and plug it into this equation here. So that's what we've done here. Again, our unknowns are the u's. Everything else is known, except you know, everything else is imposed and known. And just like in the finite difference method, we put u on the left-hand side and extrapolate to the next time step. And so this is our solution algorithm for that's now a time extrapolation. So we start at time 0, and you iterate until you have your basically the end time reached. And the nice thing is, in principle, you can write it in Python, for example, directly as it's written here. And I want to stress again, so most importantly, you need the inverse mass matrix. Okay, we need the inverse mass matrix here. This is a global system of equations in the sense that it has as dimensions the entire degrees of freedom of the system. So that means if your system has 1,000,000 degrees of freedom, which is not a lot in wave simulations, these matrices K and M would be 1,000,000 by 1,000,000, or 100 million by 100 million, and that it would never work. You could never do this with, you know, matrices on a computer, because our systems are relatively small. We can write it, you know, in this way. The other point is, if M, if the mass matrix is, let's say, a not a banded, but a full matrix, which sort of in a unstructured triangular tetrahedral finite element graph, that is the case. You have to invert this huge matrix. You have to invert it once, as a preparatory step, but that's very involved. Okay, so and you would have to, employ all these linear algebra tools, and that has been one of the reasons why, again, seismologists did not really use it extensively, because that's a big overburden for complicated systems. Okay, so that's basically all. I will show you. How this looks in the code, and you can play around with this later. A few final words on the finite element method. It requires linear algebra libraries. It's kind of suboptimal for parallelization because of this matrix, this mass matrix inversion. And I say it again, many of you know this already. The key success of the spectral element method is the fact that the mass matrix is diagonal, and so the inversion is trivial. Okay, that's going to be maybe if there is one thing you should remember from this course, and if you didn't know it before, it's exactly that. The spectral element, the success of the spectral element method in the last 20 years has been the fact that this mass matrix in this particular formulation, you will see later, is diagonal, and the inversion as such is then, of course, trivial. Okay.
Heiner?
Yes.
Yeah, I'm actually a bit surprised that the mass matrix is not diagonal in the finite element method, given that it's dependent on what was it, phi I and phi j, which, I mean, like, it's as the product of phi I and phi j, which, if I understood correctly, is 0.
Not,
if I is not
well, there is an over. You have to be careful. There is an overlap. It's not. It's banded. It's
right. Okay.
There is an overlap, so it's not.
Yeah, gotcha. Okay.
Okay, and then you invert it. It's spreading out. That's the reason why the M itself is has the same structure as this, but if you invert it, it's kind of spread it out a little. Okay, so it's in any case, it's not diagonal. Okay.
All right. Thank you.
Another important aspect, and that's relevant for spectral elements as well, for spectrum, curved, not curved, or curved elements are possible. So you can use this via, a coordinate transform. So also that's a very important aspect. And there are things you can do. It's indicated here. Octree approaches, which is, changing the mesh width towards the surface. These are possible ways of changing the mesh width. But of course, things like that are much easier done with, let's say, tetrahedral grids. Okay. Any questions to this part? While you think about questions, let me just quickly show you part of the code. Let's see. I just put, okay, this is no longer active, but I just want you to show you this. This is a code FE elastic 1D solution. Maybe remember that. Now look, remember what I showed you in mathematics, and this is what you write. You can write in a Python code. I find this, it's beautiful. It's inefficient, but it's beautiful. So M inv is the inversion of the mass matrix, and
This is in Python 3. This was actually, only since Python 3 you can use this ampersand sign indicating matrix vector operation. And so you can see this is the entire 1D wave equation. Of course, there's a lot of things that happen inside here. It's not a scalar operation, it's a matrix vector operation. Now, the other thing that I find beautiful is you can write the finite difference solution in exactly the same way, more or less, and up to minus sign. So this is you can run this if you want, and you can compare the finite difference with the finite element method. Interestingly, the accuracy is more or less exactly the same of the linear finite element method and the standard classic simplest finite difference method. The only thing that's different is the numerical dispersion goes in the other direction. So while in the finite difference method the velocities were smaller, here the velocities are actually a little faster, and you will see that if you run this script. And here you can see how the stiffness matrix and the difference matrices here are initialized. This is even with H adaptivity, so you can change the math which, and something you can look at in the codes. Okay. Any questions?
Heiner,
Jack.
so in engineering problems where it's like a static stress calculation, I guess the normal like tetrahedrally meshed linear or like quadratic but low base order basis function finite element methods seem to be ubiquitous, even though sometimes they use millions and millions of cells because they're very complicated geometry. Is it just that the geometry complexity means that they have to pay that cost of bad parallelization because they need the tetrahedral meshing? Is that the reason?
And I'm not I'm not sure the experts would say it's bad parallelization. It's that problem, and then there's a lot of mathematical tools that make these matrix inversions efficient. They look at the structure of these matrices and change them in a way that you optimize the speed of the inversion. It's an own field of computational mathematics or mathematics of computations. But yes, the problem requires that, and that's why in engineering this is the standard way. And of course there is Abacus, there is huge commercial codes that are that cost a lot of money, and they're used in engineering. Other questions?
Yeah, I don't know whether you've mentioned it in the end. Now, what exactly defines the weak form of the wave equation? Now, I mean, what does it mean actually? What is the weak form of the wave equation?
Yeah, it's a basically you're projecting solution onto a vector space, and the vector space is the space of these basis functions, and so you are looking at the solution of the problem in this. You go from infinite dimensions to a finite dimensional vector space in which you look for the solutions. That's the weakness. That's the weakness of the weak solution. So it's a dimension reduction from infinity to finite. That would be my answer to that. Does that make sense? And that's the trick. That's the trick.